Find the absolute value of the difference. So first we're going to subtract. 1.1 minus 6.5 is negative 5.4. But we are using absolute value, which is the distance between that number and 0. So when you have a negative inside absolute value bars, it turns it into a positive number because distance is always measured with positives. So this would be 5.4. Keep in mind we wouldn't measure something and say that's negative 5.4 feet. We would just say it was 5.4 feet long. To answer the statistical question, is there a difference between the time it takes 6th graders at my school to finish a jigsaw puzzle and the time it takes 7th graders at my school to finish the puzzle? Eve randomly selected some 6th and 7th graders at her school to complete a jigsaw puzzle. The following table shows the time in minutes that it takes 11 6th graders and 10 7th graders to finish the jigsaw puzzle. This data would be considered a sample because she didn't ask every 6th grader or every 7th grader at her school. She only asked a small portion of the population. So she took a sample. Typically, when looking at data, we may want to put it in a display or a distribution. We can use histograms, dot plots, box plots, bar graphs, and so on. Here is a dot plot for both the 6th and 7th graders that she surveyed and the time that it took them to complete the puzzle. When looking at a data distribution, some important things to take note of are the shape, spread, and center. So if we look at this one, we could say that it is approximately symmetric. This one you might say is slightly skewed because there's some points here. The center would fall somewhere in here, and maybe somewhere in here for this one. We can be more precise by using either mean, median, or mode for describing the center. And the spread of this one, it went from 31 to 46, which is a spread of 15, whereas this one went from 44 and 28, which is a spread of 16. One way for us to describe these is using the mean and the mean absolute deviation. To find the mean, we're adding all of the values together and then dividing by how many data values there are. So for the 6th graders, we would add 31 plus 32 plus 35 and 35 because there are 2 of them, 37, 3 40s, so 40 plus 40 plus 40, 41, 45, and 46 together, which is 422. But then we need to divide by 11 because there are 11 dots. That gives us a mean of approximately 38.36 if we round. To find what's called the mean absolute deviation, we're going to take these values and figure out how far away they are from the mean. So this is called the mean. And for the mean absolute deviation, we're going to subtract 38.36 minus 31 to figure out how far away it deviates from the mean, which is 7.36. Then we'll do the same thing with 32. 38.36 minus 32 is 6.36. 35 subtracted from 38.36 is 3.36. And there are 2 of them. Here we have 37. That would be 1.36 away. We have multiple 40s. 40 minus 38.36 is 1.64. And we need 3 of them. (41 minus 38.36 would give us a deviation of 2.64. 45 minus 38.36 is 6.64. And then 46 minus 38.36 is 7.64. So we'll add all those together and divide by 11 again because that's how many values we have. This is 43.64. So to find the MAD, or the mean absolute deviation, we use 43.64 divided by 11, which is approximately 3.97 when rounded to the nearest hundredth. So in this dot plot, you see they've marked the mean at the line. Then to get this value, they've added 38.36, the mean, plus 3.97, and that gave them this value here. And then we're going to find one deviation below the mean, so 38.36 minus 3.97, which is 34.39. Let's mark those values in your book on top of 1. So 38.36 is slightly above 38. And we'll write that that is the mean. Then when we added 3.97, that put us at 42.33. That is the mean plus 1 mean absolute deviation. And if we did the mean minus 1 deviation, it put us at 34.39. In number 1, it says mark and label the following information on the dot plot. The sample mean of the 7th grade data distribution. So we also need to do 7th grade. To find the mean of the 7th grade, we're going to add 28, 28, 34, 35, 2 37s, 39, 40, 41, and 44. Which comes out to 363. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data values in this one. So 363 divided by 10 gives us a mean of 36.3. And we'll mark that in the display. So 36.3, that is the mean. Now to determine the mean absolute deviation, we need to find out how far each of these are from 36.3. So 36.3 minus 28 will tell us how far this one deviates from the mean, which is 8.3. And there are 2 of them. 36.3 minus 34 is 2.3. 35 is going to be 1.3 away. 37 minus 36.3 is 0.7 away, and there are 2 of those. 39 minus 36.3 is 2.7. 40 minus 36.3 is 3.7. 41 would be 4.7. And 44 minus 36.3 is 7.7. Add all those up, and that is 40.4. Again, there are 10 values, so we're going to take that 40.4 and divide by 10, which gives us 4.04 as our mean absolute deviation. So the mean was 36.3. The mean absolute deviation was 4.04. So we need to add those two together for the sum. $36.3 plus 4.04 is 40.34. And then the difference, so we're going to take 36.3 and subtract 4.04, which is 32.26. Then it says, use the dot plots from problem 1 to answer the following questions to examine the overlap in the distributions. Of the 11 times for the 6th graders, what fraction of the times are within one mean absolute deviation of the mean for 7th graders? Well, if we go back and look at the mean for the mean and the mean absolute deviations for the 7th graders, if we continued these lines here, we can see that there are 1, 2, 3, 4, 5, 6 out of the 11. Because it's the fraction of 6th graders that are within one mean absolute deviation of the 7th grader data. Of the 10 times of the 7th graders, what fraction of the times are within one mean absolute deviation of the mean for the 7th graders? Here we have 1, 2, 3, 4, 5, 6 again, but this time there's only 10 data points for the 7th graders. The dot plots show the actual times in seconds that passed when students estimated the length of a minute had passed. The sample mean for the data distribution of estimates of a minute when quiet is about 59.07 seconds. The sample mean for the data distributions of estimates of a minute when talking is about 64.93 seconds. What does this tell us? There isn't much space for me to write it down there, so I'm going to type it right here. The typical estimate of time for a minute was shorter when the environment or when the surroundings were quiet than the estimate of a minute when people were talking. Remember that measurement mean is a measurement of what's typical for the data set. So the typical time that people estimated a minute was shorter at 59.0 seconds than when people were talking. Calculate the difference between the sample mean when quiet and the sample mean when talking. What does this tell us? When we subtract, we get 5.86 seconds of difference. This tells us that the student In a quiet environment, typically estimated a time that was 5.86 seconds shorter than students in an environment with people talking. Than the talking environment. The typical distance is about 2.66 seconds from the mean time of 59.07 seconds for the estimates when quiet. The typical distance is about 2.8 seconds from the mean time of 64.93 seconds for the estimates when talking. What does this tell us? The distance from the mean times to the data points is the MAD, or the mean absolute deviation, and that tells us about the variability. And since it's 2.66 and 2.80, we would say that the variability in times is similar in the two distributions. Four says, mark and label the following information on the dot plots. The mean of the data distribution with more variability. Well, in here, the one with more variability is the talking amount. So the mean should be at 64.93. The sum of the mean and the mean absolute deviation of the data distribution with more variability. Well, the variability for that was 2.80. So we're going to add 2.80 to 64.93. Which is 67.73. And the difference, so we're going to take 64.93 and subtract 2.80, which puts us at 62.13. We have 1, 2, 3 inside the deviation out of 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 points. So 3 out of 14. What fraction of the estimates of a minute when talking are within one mean absolute deviation of the marked mean? Here in the talking, there's 1, 2, 3, 4, 5, 6, 7, 8 of the points are within one mean absolute deviation out of 9, 10, 11, 12, 13, 14. So mean absolute deviation is a way that we can compare variability, and we can compare the means to look at two different populations.